Good day, listeners.
I'm Mark Elizar Tyson.
I'm Christoph Miguel Cabuag.
And I'm Jonel Labarda.
And
we are Group 14.
And we're about to present all you need to know about
Precast and pre-stressed concrete.
So what is precast concrete? Precast concrete, also known as prefabricated concrete, is a construction product produced by casting concrete in a reusable mode or form which then is cured in a controlled environment, transported to a construction site, and lifted into place, which then means that precast concrete elements can be joined to other elements to form a complete structure. It is typically used for structural components such as wall panels, beams, columns, floors, staircases, pipes, tunnels, and so on. Now, before we move on to the next topic, let's first talk about how precast concrete was invented. So it started at ancient Rome when they began developing forms and molds, allowing them to shape the concrete into many sizes and use them throughout their building processes. One of these molds involves the innovative network of tunnels and aqueducts they constructed. Many of ancient Roman infrastructures were based on this precast innovation. This continued at modern England, specifically in Liverpool around 1905, and as mentioned, John Alexander Brodie was at the forefront of prefabricated housing technology, promoting the use of precast reinforced concrete slabs as a means of building houses quickly and cheaply. This innovation then expanded to New South Wales government railways, where the first precast concrete station building to be constructed by the New South Wales Railways was opened at Lake Cargelligo in March 1918. The use of precast concrete for station buildings ceased after 1932 but continued in use for signaling buildings after this time. It was then when the Precast Concrete Institute was established on June 18, 1954 to serve as a tactical sounding board for all information and practices related to precast or pre-stressed concrete. Since its founding, the PCI has developed, maintained, and disseminated the body of knowledge for the precast and pre-stressed concrete structures industry, and hence created and maintained many industry standards. Today, precast is widely used in the construction of the superstructure or frame of a building, and due to its versatility in shape, texture, and color, it's often used as architectural cladding designed to mimic the aesthetic design of more expensive materials, and since precast concrete can serve as both structural and architectural elements of a building simultaneously, whole stable structures of complex design can be made using precast concrete. Now that we already know the precast concrete uses molds to create formations for a specific structural element, it is right to move on to our next topic, formworks. So what are the types of formworks? The first type is the traditional timber formwork. Timber formworks can be constructed at a lower initial cost than steel due to higher availability and cheaper production cost, but has a shorter lifespan. People new to building formworks typically choose timber because it requires no special tools nor a high level of construction experience. Next is the engineered formwork system. And basically, this type of formwork doesn't need to be dismantled thoroughly as it only uses modular systems such as pin, clip, or screw to hold the formwork together, and the precast concrete is designed to be mass-produced product. Third is the reusable plastic formwork. Similarly as the timber formwork, but not as versatile as it due to the prefabrication requirements and is best suited for lost cost repetitive structures such as mass housing schemes. So here are the pictures of first the traditional timber formwork, the engineered formwork system, and the reusable plastic formwork. So moving on, the fourth type is the permanent insulated formwork. Because of the advantages in terms of speed, strength, thermal, and acoustic insulation. However, no applications of additional reinforcement within the structure. Insulating concrete forms are mostly designed as walls. The fifth is the stay-in-place structural formwork systems. This is used mainly for concrete columns and piers and stays in place, acting as permanent axial and shear reinforcement for the structural member. It also provides resistance to environmental damage for both concrete and reinforcing bars, such as corrosion and freeze-thaw cycles. Lastly, is the flexible formwork. Fabric formwork technology is one such system of molds that involves the use of geotextiles to create flexible shape precast concrete of high density external microstructure, thereby increasing durability and creating highly optimized, architecturally interesting building forms. So here are the examples of the permanent insulated formwork, the stay-in-place structural formwork systems, and the flexible formwork.
Now that we are done with the introductions regarding the precast concrete, we move on to the precast concrete structural elements. Within this topic, we are obliged to describe the observable characteristics, limit specifications and designs, and different types under each structural element. To start, we have the precast slabs. Precast slabs are cast in factory environment and include the following pre-stressed concrete options. Hollow core units. A hollow core slab, also known as voided slab, hollow core plank, or simply a concrete plank, offers the ideal structural section by reducing the dead weight while providing maximum structural efficiency within the slab depth. The precast concrete slab has tubular voids extending the full length of the slab. This makes the slab much lighter than the massive solid concrete floor slab of equal thickness and strength. Double T units. Slabs are two symmetrically placed beams interacting with a slab forming in one section with a double T shape made in precast, or pre-stressed concrete. Double Ts are manufactured in factories. The process is the same as in other pre-stressed concrete manufacturing by building them in pre-tensioning beds. These slabs are manufactured with inherent resistance to moisture and corrosion, making its use ideal for parking garages, office buildings, commercial buildings, factories, and industrial buildings. Specifications include fabrication with G50 concrete and 1/2 inch strands ASTM A416 as standard. Each double T slab is normally 2,400 mm wide. Solid concrete units. These are simple solid core slabs which appear same as solid slabs cast in situ. The only difference being that they are prefabricated. Slab depths range from 75 mm to 240 mm with upstands, giving overall depths between 150 mm and 300 mm. Slab widths usually manufactured to 600 mm or 1200 mm nominal size. Rapid construction. Precast slabs are manufactured to the specific needs of the building, eliminating shattering and adding the speed of construction. Design efficient. Composite floors can be designed to act compositely with the structure of the building to reduce member sizes. Soffit finish. The soffit, or the underside of the architectural structure of a solid pre-stressed slab, is generally from steel mold and is therefore suitable for an exposed finish in structures such as car parks, industrial buildings, and for a wide variety of applied finishes in other types of buildings. Precast beams. Beams are used for suspended flooring. Beams are typically used as ledges for forms in precast flooring to sit on, but can also be used as flooring and be reinforced or stressed. Rectangular beams. Rectangular beams get their name from their end profile. These beams are generally used to span clear sections and are reinforced or pre-stressed. Typical beam width is 12-inch or 16-inch, spans up to 50 feet. Typical designation would be 16 RB24 or 16 in width in inches and 24 in depth of inches. L and IT beams or inverted T beams, typically used to support slabs, walls, masonry, and beams. Typical beam width is 12-inch and depths of 20-inch, 28-inch, 36-inch, 44-inch, 52-inch, and 60-inch. T-beam or DT. T-beams, either single or double, cover the span range beyond slab-type members such as hollow core planks. The top of the T-shaped cross-section serves as flange or compression member in resisting the compressive stresses. T-beam. T-beams, either single or double, cover the span range beyond slab-type members such as hollow core planks. The top of the T-shaped cross-section serves as flange or compression member in resisting compressive stress. For double, spans up to 100 feet and typical width would be 8 feet and depths would be 12-inch, 18-inch, 24-inch, and 32-inch. The designation would be 8DT24 plus 2 or 8 in width in feet, 24 in depth, and plus 2 would be 2-inch topping. For single, spans up to 120 feet, typical width would be 8 feet, and typical depths would be 36-inch and 48-inch. Designation would be 8ST36 plus 2, or 8 in width in feet, 24 feet in depth, and plus 2 meaning 2-inch topping. Precast columns. Precast concrete columns are modular in design in order to be made into different heights. Widths are 12-inch, 18-inch, and 24-inch. Columns are only structural if a structural engineer has adapted them to a building. Precast column can be produced as either single-story corbel column or multi-story corbel column. Columns can be either rectangular or circular in section. Projecting rebar can be provided for tying in or in situ floors. Options for foundation connections include cast-in base plates, dowel tubes, or projections. Beam support is achieved by columns with flare heads, corbels, or bolt-on brackets. With flared heads, for radial design for supports within, in other words, support for beam and floor slabs, corbels for biaxial supporting, and bolt-on brackets for steel beam connections embedded within the structure. Precast concrete walls. Precast concrete wall systems offer wide variety of shapes, colors, textures, and finishes to the designer. As a result, the assessment of samples is a key component in the use of precast concrete. Precast infill walls or load-bearing walls. The infill wall is a supported wall that closes the perimeter of a building constructed with three-dimensional framework structure, generally made out of steel or reinforced concrete. Infill walls contribute to the construction framework by bearing loads from other structural elements and has the ability to carry its own dead load. Cantilever walls, also known as gravity walls, are relatively rigid walls used for supporting the soil mass laterally so that the soil can be retained at different levels on two sides. Being stuck together, they lock into place and form a setback that allows the wall to be supported by the pressure of the soils behind it. As such, retaining walls are engineered for more specific purposes like hillside farming and roadway overpasses. Panel walls. A wall panel is a single piece of material, usually flat and cut into rectangular shape, that serves as the visible and exposed covering for a wall. Panel walls are mostly used in modern architecture because of its minimalist design, though patterns of intricacy may be added. The maximum practical size for wall panels has been suggested to be 24 inches by 8 feet to allow for transportation. Precast staircase. Precast concrete staircases provide unobstructed, early, secure, and instant work platform during construction. This solid footing helps speed up construction and provides a safer working environment by allowing immediate access to be gained. As precast concrete needs no additional curing on site and does not require protection from weather conditions, the installation process is quick, neat, clean, and dry. Precast concrete properties. Here, we have listed the properties unique to precast concrete. First would be structural capacity. Structural precast concrete panels are strong, durable, and versatile building material, particularly suited to harsh climatic extremes and requiring minimal maintenance. They can be engineered to meet the structural needs of every type of domestic construction. Precast finishes are highly impact resistant, withstand wear and tear, and require minimal repairs and maintenance. Thermal mass. Precast delivers high standard internal finishes of the form, with the mold providing internally exposed thermal mass at low cost without the need for insulation or other linings. Fire resistance. Precast panels are highly fire resistant with zero flammability on both external and internal surfaces. The BCA specifies the fire resistance level required in various applications in terms of fire resistance periods, or FRP, for structural adequacy, integrity, and insulation. Durability and moisture resistance. While dense precast concrete is generally not subject to rising damp or structural damage from condensation and dew point formation, no type of construction is immune, but precast is rarely affected by water vapor passing through the material. Surface condensation or dew point formation is more common, and while often causing unsightly mildew and stains, structural damage in precast concrete is unlikely. Last would be appearance. An almost endless variety of shapes, colors, textures, and finishes are available for precast concrete. It can be molded and shaped to suit almost any design or form. Off-site precast factories may be used to operate complex or detailed methods and finishes to obtain a high degree of quality control in a controlled environment.
So now, let's move on to the advantages of precast concrete. Number 1, precast concrete is comfortable, meaning the material has intrinsic properties of thermal inertia, allowing a more constant temperature in both cold and hot regions, and acoustic insulation. Number 2, precast concrete is safe. Everybody knows that concrete does not burn. Not only is the structural stability maintained for longer periods, but concrete construction prevents the spread of fire from one building to another. It is sufficiently strong to resist impacts, blasts, and natural catastrophes like earthquakes, tornadoes, and floods. Number 3, precast concrete is versatile. Factory production allows a wide choice of surface finishing, color range, and special shapes. Precast concrete has another advantage, is moldability, which entails designers to copy classical details like keystones and capitals or match the finish of materials like weathered stones. The precast concrete industry can source a wide range of aggregates locally and offer a tremendous variety of colors and visual effects. Number 4, precast concrete is healthy. Indoor air quality is a concern for all of us. Precast concrete is stable throughout its life and does not need chemical treatment to protect it against rot and insect attacks. This means that there are no emissions in the internal environment. Number 5, precast concrete is optimized. Advanced technologies used in the precasting plants create an improved quality product compared with cast on-site concrete. Additionally, this quality can be checked before a unit is inserted into the structure of site work. Number 6. Precast concrete is durable. Concrete lasts for years. Egyptian and Chinese people used an ancient form of concrete for buildings and structures that still exist today. Concrete is used where the structural stability has to be maintained for long periods. Effective detailing helps to lengthen the life of a concrete building. Precast manufacturers can offer guidance on designing for durability. Number 7. Precast concrete is ecological. Made of natural raw materials such as stone, gravel, sand, and cement, locally available almost everywhere in an enormous quantity. Precast concrete minimizes the whole life cycle impact on the environment when compared with other construction materials. Precast concrete units can be entirely be reused or recycled. Number 8 is precast concrete is fast. The top floor of a skyscraper can be cast in the factory when the foundations have not yet started. But the project requirements of a modern construction prefer a just-in-time delivery. On-site production using precast concrete is not only faster but also safer as our secure working platforms are quickly established. 9. Precast concrete is affordable. Precast concrete combines the excellent quality of factory production with a relatively inexpensive material. The cost to repair and maintain as a concrete structure are highly limited. There is therefore no need to compromise on quality to reduce costs. Simply choose the best way to locally available resources. And last but not the least is precast concrete is sustainable. Sustainable means a three-win situation for all three pillars of our society: people, profit, and the planet. If only one of these elements is negative, the solution can be considered sustainable.
Precast versus pre-stressed. Precast refers to any piece of concrete that is cast at a different location from the final building site, and the cured piece is transported to site when the site is ready for delivery, whether it is pre-stressed or reinforced with conventional reinforcement bar. This is compared to the alternate method of cast in place, where forms are assembled at the building site and ready-mix concrete trucks deliver the wet concrete to be placed, and once the concrete is cured, the forms are removed. Pre-stressed concrete is primarily a form of precast concrete. The basic idea of pre-stress plays on the desirable attributes of concrete and steel. When you concentrate the steel cables toward the bottom of the member, you can create an upward force from the pre-stressing, resulting in compression on the bottom and tension on the top, or better known as camber, as we can see in the picture. Now when this member is loaded up and wants to bend and deflect, it wants to put the top into compression and the bottom into tension. So the applied load must overcome the counteracting force already in the member for the pre-stressing. This method uses the tension properties of steel but not to take advantage of the compressive properties of the concrete, only to resist the load. To pre-stress a piece of concrete, first, the steel strand made up of individual cables are woven together, are stretched and held in that position, or you can imagine when you pull on a rubber band inside of the form. Then concrete is then cast around these steel cables and left to cure and bond to the steel cables. Once the concrete reaches sufficient strength, the steel cables are cut away from the supports, holding them in their stretched position or letting go of the rubber band. Pre-stressing. Furthermore, pre-stressing is the introduction of a compressive force to the concrete to counteract the stresses that will result from an applied load. There are two methods of introducing pre-stressing to a concrete, namely pre-tensioning and post-tensioning. What is pre-tensioning? Pre-tensioning happens before the casting of the concrete. This is done by placing of high tensile steel tendons in a desired profile in which the concrete is to be cast. When the concrete had reached the required strength, the tendons are released to introduce a compressive force to the concrete. The concrete will then be in a permanent state of maintaining pre-stress strength. What is post-tensioning? Post-tensioning is the process of introducing compressive force to the concrete after the concrete is casted. This is done by placing high tensile steel PC strands tendons are normally inside the ducts that were casted into the concrete in a desired profile. The tendons are then stressed and locked with anchors. This application introduces compressive force to the concrete, and the concrete can then achieve its required pre-stress strength. There are two kinds of post-tensioning. First is banded post-tensioning. Banded post-tensioning has pre-stressing tendons permanently bonded to the surrounding concrete by the in situ grouting of their encapsulating ducting following tendon tensioning. This grouting is undertaken for three main purposes: to protect the tendons against corrosion, to permanently lock in the tendon pre-tension, thereby removing the long-term reliance upon the end anchorage systems, and to improve certain structural behaviors of the final concrete structure. Banded post-tensioning characteristically uses tendons, each comprising bundles of elements placed inside a single tendon duct with the exception of bars, which are mostly used unbundled. This bundling makes more efficient tendon installation and grouting processes, since each complete tendon requires only one set of end anchorage and one grouting operation. The second kind of post-tensioning is unbanded post-tensioning. Unbanded post-tensioning differs from banded post-tensioning by allowing the tendons permanent freedom of longitudinal movement relative to the concrete. This is most commonly achieved by encasing each individual tendon element within a plastic shearing field with a corrosion-inhibiting grease, usually lithium base. Anchorages at each end of the tendon transfer the tensioning force to the concrete and are required to reliably perform this role for the life of the structure. Unbanded post-tensioning can take the form of individual strand tendons placed directly into the concrete structure in buildings, ground slabs, or bundled strands individually greased and shaped, forming a single tendon within an encapsulating duct that is placed either within or adjacent to the concrete. For example, is restressable anchors external post-tensioning. Unbanded post-tensioning differs from banded post-tensioning by allowing the tendons banded versus unbanded. The benefits that banded post-tensioning can offer over unbanded systems are reduced reliance on end anchorage integrity, increased ultimate strength in flexure, improved crack control, and improved fire performance. The benefits that banded post-tensioning can offer over banded systems are ability to be prefabricated, improved site productivity, improved installation flexibility, reduced concrete cover, simpler replacement and/or adjustment, superior overload performance.